Hello, my name is Rashid. I am from presenting. I'm going to introduce to torque and line of action of the force and lever arm. The first topic is the torque moment. The torque moment, also known as stringy moment or simply torsion, is a concept used in physics and generics to describe the effect of a force applied to reading object that tends cause it to rotate about in axis. It is defined as a product to a plate force vector and the distance vector from an axis of rotation to the point of collision for a force, multiplied by the sines of the angle between these two vectors. Mathematically, the torque can be expressed as tau equal r by multiplied for f, where tau represents the torque, r is the distance vector from the axis of rotation to the force application point, and f is the applied force vector. Next topic is the line of actions of the force. The line action of the force is an imaginary line that indicates the direction in which a force applied to an object acts. It is a straight lines that extend along the direction of the force and pass through a point of application of side force. And the line of action of the force is independent of the magnitude of the force and uses the determinative effect of the force on the object. If the several forces are applied to an object, the result in the behavior of the object will depend on the lines of action of those forces and how they combine with each others. And the final topic for my part is lever arm. The lever arm, also known as the lever moment of the moment of R, is a measure of the perpendicular distance between the point of application of the force and the axis of rotation of fulcrum around which the force acts. In simple terms, is the distance between the point application of the force and the axis of rotation. The lower mass is important considered in the analysis of mechanical systems, science of determinate magnitude, on the moment of the torque generally by a force. The moment is calculated by multiplying the magnitude of the force by the letter arms. And mathematically, the moment or torque can be expressed as tau equal for F um, by multiplicator D, whereas the F is the magnitude of the force and the leg and the D is the leg of the lever arm. Thank you for watching.
Hello, my name is Carlos. Today I'm going to talk about the torque movement, but in this case with an angle. We know the torque movement is a force that causes rotation about an axis, and to calculate this torque, we need two principal factors: the applied force and the distance between the axis and the point of application of the force. The formula, as you can see in the image, is torque equal radius plus force plus sin of the angle. Um, as we can see in the image, we have the r, that is the distance between the point of rotation and the force. The o is the axis, that is also the same as the point of rotation, and we have the force. The force is divided in the two components, like fx and fy. As we can see, fx is doesn't applying like a force because it's in the same direction as the distance. But we have fy that we can see that is applying a different force in a different angle. So we are going to use f sin to um, to resolve the system. Also, we have the torque resultant. That is basically the sum of all the torque that is in the system. To calculate this, we need to know to, to do some steps. Like the first one is identify all the forces that are applied in the system. and determine magnitudes, angles, directions, points of applications. Also, we need to calculate individually the torque caused by each force, and we need to be conscious about if the torque is positive or negative depending of the direction of the rotation. Okay, and the last part is just sum the torque, the all the torques, and we will have the torque resultant. Well, as we can see in the image, we have a diagram of uh, torque resultant. We can see that in the zero of the bow, we have the axis, and we have two other different torques. The first one with a force of 100 newtons, and the other one with 80 newtons. We can also see the direction of both are to the counterclockwise, and we have a different distance between the axis for the force one that is 250 millimeters, and the other force two for the axis that is 200 millimeters. So to resolve that, first we need to make uh, first the torque of the force one, and second we need to resolve the other torque. And when we finish, we're just going to sum the torques. Some strategies for resolve this kind of systems. First, we need to identify the system. Second, we need to check where is the point of rotation, or in some cases, where we are going to choose where is the point of rotation. Second is make a more clear diagram. Third, is identify the relevant forces, because sometimes in some occasions there are forces that is there are not necessary in our diagram. Fourth, we need to calculate the torques individually. And the last one is sum all the torques. Just remember, as I said, we need to check that if one torque is going to the clockwise, is going to be negative, and if it's going to the opposite side of the clockwise, is going to be positive.
Translational equilibrium refers to the state in which the combined effect of all forces acting on an object results in a net force of zero. This condition ensures that there is no overall acceleration in any direction, and the object remains either at rest or in uniform motion. Mathematically, this equilibrium is expressed as the sum of fx is equal to 0 and the sum of fy is equal to 0, where the sum of fx represents the sum of all forces in the horizontal direction, and the sum of fy represents the sum of all forces in the vertical direction. The second condition required to achieve equilibrium involves maintaining a constant angular velocity and preventing accelerated rotation in a rotating body or system. If the rate of rotation remains unchanged despite the forces acting upon it, the system can be said to be in equilibrium. To summarize, in order to achieve equilibrium, the total sum of moments acting on the object must be equal to zero. Here are the strategies we consider to solve this type of problem, which are identify the force involved, select a reference point, compute the moments or torques, apply the second condition of equilibrium, solve the questions, and verify the solution. Now, in this example, I put as object a metal lever that rotates in an axis C, and the weight of the bar is the 6 newtons that are in the middle of the lever, while the 3 newtons are an external force. The first thing I did was calculate the force in R, given that it's mentioned that the lever is in equilibrium. For this, I simply made the equation and queried it. I did something very similar to find the moments. I used the formula that we have already seen to remove each moment and verify that the condition is met. As a note, it should be clarified that the moment at r is 0 since it has a distance of 0 from the axis.